So, we talked last time about just how does stuff get started out in space? Most everything exists as gas in these giant clouds called. You probably all said the right thing, but I couldn't hear it. Out there, the big clouds of gas and dust, what are they called? Molecular clouds, nebula, right? And then we go from nebula and we start to, something's got to put energy into the system, it's got to shock it, and so things start to kind of move and combine, and we start to get these little things. What are they called? Okay, we got filaments, and inside the filaments you have clumps. And inside the clumps you have cores. So just to review that, you've got nebula. Inside the nebula you get filaments. Inside the filaments you get clumps. Inside the clumps you get cores. From the core you may or you'll get a protostar. If this thing gets hot enough and it starts fusion, then you'll get an actual star, right? If it doesn't, then you'll get a brown dwarf. This is not everything you need to know about this. That's all last lecture. This is just to kind of catch us up. And so we saw that at the nebula level, man, it's just like, it's just gas and dust just everywhere. At the filament level, there's gas and dust everywhere, but it does kind of, you start to get like these strands, right? And that's what this is made up of primarily. But then at the clump level, if you were to kind of look in your gas and dust strands and filaments and things, you're going to get areas of high concentration. These are going to be much more dense, these are going to be much hotter. Then within these you may have cores. Now, at this level it's still very much just globular, like kind of, it's not necessarily perfectly round, it may be a little amorphous, but it's large, it's 3D, and if you had to describe it, you might describe it more as just like a big ball. By the time you get to the protostar, some things are happening, things are changing. Because something's happening at every level here, and it's the idea of this angular momentum. Everything here is rotating, okay? And this rotation really has a big impact. It's an R, by the way. This rotation has a huge impact. These things are spinning. Well, it's this idea of angular momentum. We talked about, and you saw in the video, how a figure skater, when their arms are out, they're spinning, right? But then when they bring their arms in like this, and you were just waiting on me to look like a ballerina today, right? They spin fast. But if they want to slow themselves down, they shoot their arms back out, and they slow back down, okay? And so this thing's spinning, it's got all kinds of energy. But when I reduce that energy down to a smaller and smaller space, it spins faster. It's the same amount of energy, but it's spinning in a smaller space, smaller diameter, smaller radius, and so it has the same amount of energy, but much faster spin. At this protostar level, if you were to look at it on its edge, you start to see something like this happen. There's a central core, star, protostar, and then there's this disk. This is generally referred to as an accretion disk. That's a word worth us knowing, accretion disk. Let me make sure that I'm writing all of this on the site that can be seen on the video. Oh, I'm doing good, okay. Sometimes I'm not. Okay, so we've got this accretion disk. If you were to look at this now, flat-wise, there's definitely going to be a greater mass here. There's just stuff here. It's kind of forming bands, right? Now, the center of this is where we got last class. in this accretion disk, the innermost part accretes. That word means like to be added to, okay? It's coming together. It's accreting to the star. So by the time we're really doing the star thing, you kind of have this, if you were to look at it like crosswise. Like, it's going to be fairly clear right around the star because that's all been brought in by gravity, but you've got other stuff happening out here. And this is where the planets will come from, okay? So the star comes from the inner part, the planets will come from this outer part, and that's really where we're going to pick up today, is with the idea of the formation of planets. How does just all this junk out here turn into Jupiter and Earth and asteroids and meteors and meteorites and comets, okay? So that's the core of today's lesson, is how, from this stage, how do you get the rest of the solar system? Our solar system or any solar system. I want to emphasize this to you. Ain't nobody seen this. Nobody's ever watched this happen. We're looking at what is out there in the universe. And we're making observations and we're making certain assumptions, right? So bear that for what it's worth. Any theory and hypothesis is subject to change with new information, right? Depending on your point of view, you may be looking at this going, okay, how did this happen over billions and billions of years? Or depending on the other point of view, you might go against and go, well, how did God do this? Okay. Am I okay to erase this? Cool. All right.
In the past few decades, our spacecraft have visited many exotic locations in the solar system, including icy comets that have orbited the sun since the planets were still taking shape. We have explored relatively tiny asteroids, ancient rubble piles held together by weak gravity. And we have found that the largest asteroids resemble the building blocks of planets themselves, all of which suggests that these objects offer clues to how the planets formed. And we have even found evidence for a violent rearrangement of the planets. Computer simulations allow us to reconstruct the formation of our solar system 4.6 billion years ago. We use the laws of physics to create these virtual experiments in order to figure out how planets took shape. After the sun ignited, most of the material around it had flattened into a disk of gas and dust. We can zoom into a simulation of a portion of a thin disk, a small piece of the universe in a box. Here, a dense swarm of objects clump together to form what astronomers call planetesimals. This simulation addresses how planetesimals form from much, much smaller particles, the size of pebbles. Pulled together by gravity, some planetesimals formed the planets, while others became asteroids and comets and dwarf planets. As the planets accreted, they carved out gaps in the disk. But the solar system remained quite cluttered. If we look at the orbits of the planets and accelerate the passage of time, so 1 million years pass by every 10 seconds, we can watch how the debris cleared. In this simulation, the giant planets, Jupiter, Saturn, Uranus, and Neptune, shift their orbits, and many unlucky asteroids and comets and dwarf planets get kicked out of the solar system. The migrating giants wreak gravitational havoc. The distribution starts out quite flat, but as most small objects get tossed out, others settle into stable orbits that allow them to coexist safely with the planets. But their orbits aren't as flat as the original solar system. Instead, they follow trajectories far above and below the plane of the planet's orbits. Today, the orbits of Pluto and other Kuiper Belt objects show exactly this pattern. The tiny icy worlds that inhabit the outer reaches of the solar system provide evidence for an ancient interplanetary transformation.
Okay. I'm going to say this, depending on what book you read, who you listen to, what video, some of these terms get used different ways. Okay? I'm not so concerned that you know the word planetesimal and have a precise definition of that. What I am concerned with is that you understand just the basic, that the concept is that you've got this dust, you've got this gas, you've got this stuff, and due to gravity, some of it begins to clump together. They're calling it planetesimals. The word planet means wandering, right? So these things are just moving around in a disk, right? Of course, our idea was that we've got a star here, and we've got this disk. It's one, you know, you've seen stuff like this. Where do you see this in our solar system? Like something that looks just like this. Saturn, right? We see this on multiple levels throughout the universe. You've got this idea of stuff that's whirling around. Well, in this case, we're saying that inside of these bands, you get smaller clumps. Well, some of these clumps will gather together, or they will quickly gather up the material that's around them. They'll get bigger, they'll get bigger, they'll get bigger. How big can they get? We could be looking at something the size of a rock. We could be looking at something the size of Jupiter, right? I mean, depending. So that's the idea here, is that these little clumps called planetesimals, like that just means like tiny wandering things. They grow, they accrete to become planets, asteroids, comets, rocks. Most debris, most of what's here is actually, it doesn't remain. When we look at our solar system now, you don't see anything nearly this dense, right? They did show you though that if you were to look at the orbits of all these things and trace them out, at least at that level, it does start to look like this. Most of this space is going to get cleared out. Most of the planetesimals literally get shot out. It has to do with gravity. Apollo 13, y'all ever heard of Apollo 13? There's a movie about it with Tom Hanks. So they lost power, and yet they had to get home. Like they're just out there in space, you have a limited amount of time, limited supply of everything. How are you going to get home when you have no power? What they did was they used the gravity of the moon. Let's do this. Here's sun, here's Earth, here's the moon, and here's them. I forget exactly, they had a little tiny bit of power. They had to use the little tiny bit that they had at just the right time so that they could slingshot off of the moon's gravity and back towards Earth. And I say that just to emphasize that gravity can be quite a force. The gravity of one object will impact the trajectory of another. And so if they'd have missed here, if they'd have miscalculated this on Apollo 13, those astronauts could have shot right out of the solar system if it hit the wrong direction. So the idea here is that as all these objects are going around and they impact each other, some of them are getting shot off, or shot out, or shot in towards the inner planets, towards the sun. You would imagine many of them with the gravity of the sun being drawn in and burning up. There are other videos I could have shown you here. I looked at many, trying to pick out the best, most concise one. Some of them are envisioning, how are you, sir?
Good, buddy.
I'm well. Some of them are envisioning, these little planetesimals hitting some of the early formed planets and adding material to them. Let me give you this at the end if you want to see just kind of where this stacks up overall for your grade with everything I'll show you, okay? You can see. All right. More or less, I think this covers this. Do you have any questions about this? We're not done. I'm going to show you one more video, okay? On the idea of exoplanets. Exo means outside of, so planets outside of our solar system. Now, this is talking exclusively of the formation of our solar system, but this is, this is how scientists believe that any solar system begins. You remember, again, you've got a nebula, it's got filaments, you start to get clumps, you get a core. The core has a disk around it, an accretion disk. The inside of that accretion disk becomes part of the star. The rest of it, now planetesimals form, they accrete, become planets, comets, asteroids. By the way, this is why they were saying, hey, we want to study these asteroids. Because they're saying, hey, these asteroids, if this theory is right, then these asteroids would be made out of the same stuff that the planets were, because they're coming from that same accretion disk. The debris gets cleared. Most of these things just get shot off into space. The remaining objects settle into, ultimately, their stable orbits. Of course, most of them are orbiting in that same plane that they imagine the original disk was, but not all of them. Some of them, because of gravity and because of other interactions, you just imagine things hitting each other. Some of them have eccentric orbits. Some of them have orbits just slightly outside of that plane. All right, I'm going to show you one more video.
This is the newest planet, an amazing image containing thousands of stars that contain a handful of the solar planets it will soon discover. Welcome back to Launchpad. I'm Christian Reddy, your friendly neighborhood astronomer. The Transiting Exoplanet Survey Satellite, or TESS, was launched in April 2018 and spent the last 4 months getting itself into the right orbit and generally commissioning its instruments and getting ready for science observations. On August 7th, TESS completed its first set of science observations, and NASA released the resulting images, and they're spectacular. The image was taken with TESS's 4 onboard cameras, each of which contained 4 detectors mounted in a 2x2 array. The result is a wide-field image that is 24 degrees across and spans up to 96 degrees from the ecliptic to the poles. That's an enormous strip of the sky. The first image is dominated by the large and small Magellanic Clouds. These are small, dwarf, irregular galaxies that are satellites to our Milky Way. They're home to hundreds of millions of stars and lie about 160,000 light years from Earth. Just north of the small Magellanic Cloud is a globular cluster called NGC 104, also known as 47 Tucanae. This is a swarm of several million stars that are a mere 10,000 light years from Earth. There are several other globular clusters in the images, as well as some distant background galaxies. But the real stars of this image are the stars of this image. Some of the stars, like Beta Gruis and R Doradus, are so bright that they saturate the detectors, causing electrons to spill over into the adjacent pixels. TESS does its work by making several images of the same sector of the sky at any given time. First, it completes a sequence of 2-second exposures that are combined to form a single 20-second exposure. The light from about 1,000 pre-selected stars are measured and recorded. These stars are being monitored for sudden variations in their brightness over time. These brightness variations are usually caused by fluctuations on the surfaces of the stars. This allows astronomers to probe the interiors of these stars and understand their internal structures. This is called astroseismology, and it's a great way to learn about a star from afar. See what I did there? I said star. Okay, fine. 60 exposures are combined to form a single 2-minute exposure, which then gets automatically scanned for the periodic brightness fluctuations in several thousand stars at once. These are the telltale signals of a planet transiting across its host star, subtracting just a tiny fraction of the star's light. After 1,800 exposures, they're combined to form a single 30-minute exposure, which is stored on board the spacecraft along with the rest of the star monitoring data. Then the process repeats again for about 2 more weeks until the spacecraft returns to its closest approach to Earth and downloads its data when the data rate is the highest. Then it swings back out high above the Van Allen radiation belts and begins another 2 weeks of science. TESS spends about 27 days monitoring each sector of the sky. Then it pivots by 24 degrees to begin a new sector. As a matter of fact, as of this filming, TESS is already working on Sector 2. After a year, TESS will complete its survey of the southern sky. Then it'll flip 180 degrees and begin its survey of the northern sky. After its 2-year mission, TESS will have observed about 85% of the sky, examining over 200,000 stars for nearby exoplanets. It's expected that TESS should be able to detect anywhere from 4,500 to as many as 20,000 new exoplanets. But even if TESS ends up at the low end of this range, it will have more than doubled the number of exoplanets that have been discovered since 1992. And by the way, that's just for the nearby bright stars. The reason astronomers want to study exoplanets that are closer to Earth is because the closer the stars are, the brighter they appear, making their planets much easier to study. TESS's predecessor mission, the Kepler Space Telescope, revealed that most stars in fact have planets around them, and that most of these planets range in the size between Earth and Neptune. These are the so-called super-Earths, and we don't seem to have anything quite like that here in our own solar system. But because most of Kepler's targets were distant and therefore very faint, there was little else that we could really learn about these planets other than their sizes and distances from their host stars. But TESS will build a catalog of nearby exoplanets that can be studied in greater detail with the James Webb Space Telescope and ground-based telescopes like Keck and the upcoming super telescopes such as Giant Magellan, 30-meter, and the Extremely Large Telescope. These follow-up studies will let us learn much more about these planets, such as their masses, their densities, and maybe even their atmospheric compositions. TESS is designed for a 2-year primary mission, but it has an orbital trick up its sleeve that would allow it to remain in the exoplanet business for a lot longer. Its elliptical orbit is highly inclined to Earth's. This allows TESS to spend most of its time high above the Van Allen radiation belts, allowing it to take images that are free of noise and interference. But Earth's tidal forces will intervene and gradually destabilize TESS's orbit. But TESS's mission designers were clever enough to ensure that TESS completes 2 orbits for every single orbit of the Moon. This allows the Moon to counteract Earth's tidal forces, ensuring that the spacecraft should remain in a stable orbit for at least a decade. Imagine what we could learn if TESS was given a 10-year mission to seek out strange new worlds. So what are you looking forward to learning from the TESS mission? Let me know in the comments below, and I'll be sure to check it out.
So what do you need to take from that? It's a lot of information. First of all, this. So far as we know, most stars have planets. You need to know. That's just a fact you need to know, okay? There's no reason that you wouldn't expect that. If the theory is accurate that, we've got this glob, this protostar system, and an accretion disk is forming, right? And then later on, we've got this planetary accretion disk. Well, if this is how stars form, then why would you not think that every star would have planets, right? There would be no reason you wouldn't expect that. This would be the system. It would actually be highly strange if you ever found a planet without stars. You'd account for that, wouldn't you? Obviously, we can't see every star, and even if we can't detect a planet, that doesn't necessarily mean that there's not a planet there. But we think that most stars have planets. You just have to know that. Okay? The other thing that we really need to take away from this is how we're detecting them. Okay? This involves a lot of the stuff that we've already talked about. So you get a telescope, right? You train it in on a star, and the light from that star reaches the telescope. You have a photo sensor at the back end of this, right? And that photo sensor is able to tell you exactly how much energy is coming off this star, right? Or how much energy is at least reaching through your telescope and to the photo sensor. And based upon that and calculations, you can determine a luminosity. You can calculate the luminosity of any star, okay? So how do we detect this? Number one, we've got to know the luminosity of the star. Now, let me change this real quick. Okay. All right, so I've got to know the luminosity of a star. This is here's my star over here, right? It's putting off light consistently, right? There can be some variation in the amount of light that's coming off it based on sunspots, magnetic storms, things like that occur here. Those things are going to, and there are larger patterns to that, right? The amount of just light material, those are their patterns that our sun has them. But if I see a shorter pattern, that means essentially that something is blocking light, right? And so that something, it's got to be a planet. You're looking at the idea of a planet in its orbit from time to time coming in between you and that star. If you see if you were to graph this, that's what they showed up there, right? I'm going to do a long graph, okay? So here's my standard brightness for the star. And all of a sudden it dips. Well, if this were Earth, okay, if you were somewhere distant on one of these other stars, and you were looking back at our star, and you're seeing evidence of the planet Earth, okay? Here's the brightness of the sun, but every so often you get this dip, and then it's bright again, and then every so often you get this dip. My question for you is, what's the amount of time between these dips? Given Earth. 365 and a quarter days, right? This is what we'd call this 1 year, right? Because a year is for us, a year is the measure of time it takes for Earth to go completely around the sun. So you'd expect this to dip every year, right? Every time the Earth comes back around to the same point. Well, it's the same idea for any of these. You'll be able to see how often it passes. That'll tell you its, it'll tell you its orbit. Now, if you know its orbit and you know the mass of the sun, the star, and all these other things, you can determine maybe the mass of the planet. If there are other irregularities there, you might be able to determine there's multiple planets. Or maybe as you're looking at this, the pattern doesn't look just like this. Maybe there's like another pattern that's kind of over it, where it's doing, I don't know, something like, maybe sometimes you get like this, then you have something like this, right? Like a super dip, where these two planets, so you might have evidence of two planets, because sometimes you get a little dip, where just one planet's passing from it, and you get another little dip, and then sometimes you get this huge dip. Well, That means two planets are passing in front at the same time. That happens, right? That happens. If you were looking at Earth, there are times when you get multiple planets aligned, and people who love astronomy just go crazy about that kind of stuff. But the bottom line is, how do you determine this? Well, you must know the luminosity of the star, and then you're looking for dips in luminosity, or variations in luminosity. I'm going to say for a pattern of change in luminosity. That's your indicator that there is a planet orbiting, right? That works great if there's ever a planet passing, this is you, here's you, right? You're looking at this star, you get a dip because a planet's passing between you and the star because of the direction you are facing this ellipse. But what if you're looking at the star the wrong way? What if it's just not oriented towards you the right way? What if it has planets orbiting it like this? Or maybe more like if you were on such a way that its orbit went like this, you would never see that planet, right? You would never see that planet at all because there'd be nothing to block it. So just because you can't see a dip doesn't mean that there's not a planet. It just means that you're not in the right orientation relative to its disk. Questions?